Imagine standing before a mirror that does not reflect your face, but instead reveals the memory of existence itself. A mirror that does not show the present moment, but gathers ancient light that has traveled for billions of years across an expanding, evolving universe. What appears within it is not who you are, but what once was. A preserved version of reality encoded in photons that began their journey long before Earth existed, long before the Sun ignited, and long before galaxies took their present form. This is the purpose of the James Webb Space Telescope. Not simply a machine built to see farther into space, but a gateway into deep time itself. It is designed to look back into the earliest chapters of cosmic history, to witness the formation of the first structures, the ignition of the first stars, and the emergence of the first galaxies from primordial darkness. For decades, the standard model of cosmology provided a clear and elegant narrative. The universe began around 13.8 billion years ago in the Big Bang. In its earliest fractions of a second, space itself expanded at an unimaginable rate, stretching energy into existence and cooling as it expanded. As temperatures dropped, energy condensed into fundamental particles. These particles combined into simple atoms, mostly hydrogen and helium, filling the universe with vast, diffuse clouds of gas. Then came the cosmic dark ages. A time when the universe contained matter and radiation, but no stars. No light pierced the darkness. No structure broke the silence. Only invisible matter and expanding space existed, slowly evolving under gravity's influence. For hundreds of millions of years, the universe remained dim, quiet, and seemingly empty. Eventually, gravity began its slow but relentless work. Tiny fluctuations in density, minute variations in the distribution of matter, grew over time. Regions slightly denser than others began pulling in surrounding material. These collapsing clouds ignited the first stars, marking the end of cosmic darkness. From these first stars, galaxies emerged. According to traditional expectations, this process should have been slow, gradual, and orderly. The first galaxies were expected to be small, irregular, and chemically simple. Heavy elements like carbon, oxygen, and iron should not have existed in abundance yet, because they are forged inside stars and released only when those stars die in supernova explosions. That process takes time, millions to billions of years. The deeper we looked into space, and therefore further back in time, the simpler the universe should have appeared. But the universe did not follow this expectation. When the James Webb Space Telescope began its deep field observations, it turned toward regions once thought to be faint, empty, and unremarkable. Instead of vague smudges of light, it revealed structured galaxies existing astonishingly early in cosmic history. Some displayed clear rotating disks. Others showed bright, compact cores surrounded by organized stellar distributions. A few even exhibited spiral-like structures, patterns that should have taken far longer to emerge. At first, scientists questioned everything. Astronomy depends heavily on measuring distance through redshift, the stretching of light as the universe expands. If redshift measurements were misinterpreted, then perhaps these galaxies were not as distant or ancient as they seemed. But repeated observations confirmed the same conclusion. Independent instruments, multiple surveys, and different analysis methods all converged on the same result. These galaxies were real, and they existed far earlier than current models predicted. Some of them formed only a few 100 million years after the Big Bang. In cosmic terms, this is almost immediate. It is like discovering a fully developed metropolis in a place where only dust and scattered foundations should exist. And then came an even deeper mystery. By analyzing the light emitted from these distant galaxies, scientists can determine their chemical composition. This is done through spectroscopy, which breaks light into its component wavelengths, revealing the fingerprints of different elements. What they found challenged expectations even further. These early galaxies already contained heavy elements such as carbon, oxygen, nitrogen, and even traces of iron. But according to theory, these elements should not have existed in such abundance at that time. They are produced inside stars through nuclear fusion. When massive stars exhaust their fuel, they explode in supernova events, scattering newly formed elements into space. Only after multiple generations of stars can heavy elements become widespread. Yet here they were, appearing far earlier than expected. This suggests something profound. The first generation of stars may have formed rapidly, lived short and intense lives, and exploded in quick succession. Instead of a slow cosmic evolution, the early universe may have undergone rapid cycles of creation and destruction, accelerating chemical enrichment far beyond previous assumptions. Even more surprising was the discovery of supermassive black holes in the early universe. These objects, containing millions or even billions of times the mass of the Sun, were expected to form slowly over vast periods of time through continuous growth. Yet observations reveal that some already existed when the universe was still young. This creates a major theoretical challenge. How did something so massive form so quickly? Some researchers propose that certain black holes may have formed directly from the collapse of extremely dense regions in the early universe, skipping the gradual growth phase entirely. Others suggest that unknown interactions involving dark matter may have accelerated their formation. There are also more speculative ideas involving primordial conditions that allowed rapid mass accumulation. But none of these explanations are confirmed. The mystery remains open and actively debated. And it deepens further when we examine the shapes of early galaxies themselves. Instead of chaotic and disorganized structures, many appear surprisingly ordered. Symmetry, rotation, and defined structure appear much earlier than expected. It is as if some hidden organizing principle was already shaping matter before galaxies had fully matured. Dark matter may play a crucial role here. Though invisible, it exerts gravitational influence across the universe. Some theories suggest it does more than simply hold galaxies together. It may actively guide the formation of structure, shaping the cosmic web long before visible matter settles into place. But perhaps the most profound discovery lies not in galaxies or black holes, but in chemistry. Across vast interstellar regions, astronomers have detected complex carbon-based molecules. These organic compounds are considered essential precursors to life. They exist in environments so distant that their light has traveled billions of years to reach us. This means that the ingredients necessary for life were already present in the universe long before Earth formed. Life, or at least its building blocks, may not be rare at all. Instead, it may be a natural outcome of cosmic chemistry, widespread across galaxies and time. With every new observation, a larger pattern begins to emerge. Instead of a slow progression from simplicity to complexity, the universe appears to have reached complexity early, perhaps even rapidly. Galaxies formed faster than expected. Structures appeared sooner. Chemistry advanced more quickly. Black holes grew earlier. Everything seems accelerated compared to traditional models. Each answer generates new questions. Each discovery reshapes the boundaries of understanding. This telescope has not merely extended human vision. It has transformed it. It reveals that the early universe was not a quiet, simple beginning, but a dynamic, rapidly evolving environment filled with intense activity, violent transformations, and unexpected order emerging from apparent chaos. And perhaps the most humbling realization of all is this. Every photon captured by this telescope has traveled for billions of years before reaching us. These signals began their journey long before Earth existed, long before life emerged, and long before any conscious mind could ask what lies beyond the stars. Now they arrive here, carrying fragments of a story still unfolding. We built instruments to look deeper into space than ever before. But in doing so, we discovered something even greater than distant galaxies or ancient light. We discovered uncertainty. The deeper we look, the more the universe challenges our expectations. And somewhere within that ancient light, scattered across time and space, the true story of existence is still being written, patiently, silently, and on a scale far beyond human imagination. It is a story not of completion, but of continuation. Not of final answers, but of expanding questions. And as long as there is light traveling through the darkness, there will always be more to see.